Hello and welcome to this lecture on object dimensions and our object dimensions class. Let's get started by opening up Maya. The first thing we're going to do before we start doing any work is actually just check that everything is running. So let me just increase the text size. So now let's scroll down our window or drag that down, make everything a bit bigger and press test. Awesome. So we've now got 107 tests running in 1 second, 1.2 seconds. Brilliant. Okay, we can check everything's working as expected. Now let's go ahead and start working on our object dimensions node. Well, class. This one will not be a node, but it will be inherited and very, very useful. Okay, let's start off within our, actually we need to make it first, don't we? So let's go into nodal and base within our folder structure, create new Python file. And then we're going to call this dag underscore dimensions. Okay, and then save, press enter. Great. Okay, so we're getting a good bit of functionality that feels well named up here. Now let's go to, and what do we need? Let's go for all this. Let's copy down our docstring and our my commands import. Add that in. So this is dealing with our object dimensions functionality, this class. And let's get started in here. We're going to create a class. And we're going to call this class object dimensions. Actually, object dimension, sorry. I'm actually going to change the name of the file because we are dealing with singular here. I try to test attributes. Oh, I suppose we do have it there, but that is actually more of the class name that we're testing. We're going to call this, I try to keep a singular file naming construction going. So every time I name a file, I call it under something singular because otherwise it can become quite quick that everything becomes a bit unreadable or inconsistent with the singular and pluralized version. So we're going to put object in here and then go def underscore underscore init and then pass for the moment. Perfect. Let's do this a bit of a different way. Import my commands as m. Okay, and now first thing we're going to do, we're going to take our object dimensions. We're actually going to import that. So from modules .nodal .base .dag dimensions, we're now going to import object dimension. And now let's put that right underneath our object. Sorry, our attributes call. So again, it's another kind of subclass that gives us a bit of functionality. And this is where dep nodes do not have any dependency, and therefore anything that is so useful. But we're going to put it in here more so for consistency. So this will essentially only work for us when called from any DAG node. But let's say specifically we create another DAG node or something which doesn't need to inherit from DAG, but essentially will have DAG properties. We want to make sure that this will come through with it. So we're going to put the functionality in here and self. And then we're going to return object dimension with the self being passed. Perfect. Okay, let's jump back to our object dimensions. So now we've passed the instance of the dep node self, and we're going to accept that by taking a node. And then we're going to say self dot underscore node, because again, this isn't really for use outside of this class. We're going to call that node. Perfect. Okay, there we go. Now let's start by adding in our first bit of functionality, which we want to essentially run a little check and check that items do have form and that they are a DAG node. which we can actually do by checking that there is a world matrix, because if there's a world matrix, it means that it is within Maya in the directed acyclic graph, accepting the world position and world space. So let's jump and write def. Actually, sorry, this is going to be a property. Call this world matrix. And this will essentially just return self dot underscore node dot a dot world matrix dot exists. Because all we need to do is just check that the attribute world matrix exists. And if it does, then we can be pretty sure that this item has form. So we now can just put that in the initiate, just because, again, you don't want to be able to getting so far as using this and then realize it doesn't actually work for you. So we're going to go for if not self dot world matrix, then arrays a value error. I'm going to do 3 little chevrons and say no world matrix, and therefore no dimension found for this object. I'm going to default that if node has no world matrix. Reformat. What do you need to reformat? I have no idea. Okay, I must have missed. Maybe there wasn't a space there. Maybe I missed that. Okay. Now, to get the dimensions, what we're going to use is the XForm, the bounding box within Maya. And this is essentially, regardless of what scales or attributes that your object has within Maya, this box will essentially always surround it, and then itself, or measure itself based on the parameters of, based on the parameters of your object. Or the perimeters, maybe I should say. I mean, both actually work, but oh well. Okay, and this is how we call that again. So we've got our XForm in here, which is again from Maya commands, which again now removes the annoying grayed out highlighting of our Maya commands. And essentially we're going to pass it self.node, which will then force self.node to be a string. So if we pass this a DAG, if we pass this a sub item, a mesh or curve or any other type, it will then just give us the XForm. It will give us the bounding box. What we can do actually as well is we want to shorthand this, just for our scene especially. Go BB, bounding box, and then just return XForm bounding box. Perfect. Okay, awesome. Let's put a little bit of information in as well. So what we're gathering, and we're getting back from this bounding box, is these parameters here. So we're getting back the minimum, translate X, Y, and Z, and then we're also getting the maximum. The maximum, translate X, Y, and Z. And what this allows us to do is quite safely say within world space of what the size of our object is. Obviously, things like volume, they're a little bit harder to predict, especially if you don't have a square, because this is a square or a rectangle, essentially, that is then grouped around your item. But there are ways to do that, which again, you can kind of search online and see what method you find. But okay, now let's go down and let's work on width, height, and depth. So we've got 3 more properties here. Okay, great. So we've got width, height, and depth. And now you'll see what we're doing here is essentially what we're going to grab from our list is we're going to grab the maximum, so the third indexed item, so 0, 1, 2, 3, the max translate X, and then minus the minimum translate X. And then we're going to do that same for height. So using Y, we're going to grab the max Y and then subtract the min Y. And then the same with the Z. And that is how we are essentially getting the depth, because if we're getting the maximum X and then the minimum X, we can just essentially subtract the minimum X and it'll give us how deep our item is. Okay, great, perfect. And now to get center, we can use this method. We can use this information that we've just gathered. So another property. We'll call this center. Written in the English way, in case anyone was wondering, we spell this a bit differently to American English. They spell it ER, which annoyingly aligns with Autodesk and some other softwares, but not all. So within programming, it is a bit of an annoyance. But okay, here we go. Let's return the list because we want the center, so we want the X, Y, and Z. So what we're going to do is we essentially are going to do very similar to what we've done up here. We're going to actually copy these over. Let's copy these calculations over here. And then Control, Shift, and Alt. Press Control C, move your cursor down, and then we will just put a comma. And what we're going to do is we're now going to double tap Control, move the cursor down, press plus, and then we are going to encapsulate these calculations. We're going to add these two values together and then go divide by 2. Okay, because what we'll be doing there is we'll be getting the minimum and the maximum positions in world space of X, and then we're going to divide them by 2, getting the center point. So we're getting the center point of the object, center point of Y, center point of Z. So, and we will go X, Y, and Z. Okay, nice and simple. Should even just say the list for consistency with above. But again, output probably is what we've been using, so let's go back to that. It's quite clearly a list because we've got the closed, the square brackets. Okay, now we've got center. But again, for all of the American users out there, let's go with ER. All right, there we go. So now let's ascribe the center and the pivot properties before we go to add some actual functions. So let's do a couple more properties. So what we're doing here is we are essentially getting the rotation and the translate and rotate from an object. We are making sure that we format the object to remove any scientific numbers and change them using format into floats, denoted by the encapsulated F there within format. We're also going to use a clean DAG object because if an object has zeroed out attributes, we want to make sure that we actually get the world space attributes of translate and rotate. So for that reason, we're essentially going to create a DAG and move it into position within the group. And that will save us any issues then. So let's first add a function called, and we're going to call this, sorry, I should actually say, yeah, obviously feel free to pause the video and copy this code out. I'll make sure, there we go, it's all fit in the screen. Okay, but now let's add our copy pivot function here. This is going to take a driver object and a driven object. Okay, and so here we've got our source translate, which we are gathering using xform, where we're querying the translate in the world space of our driver object. And then what we're going to do is then with xform, change the pivot using the pivots argument to that source translate. Simple, nice and easy. And now let's create a few more functions. And these will essentially copy the pivot around for us depending on which direction we want that to go. Let's copy pivot 2. I'm going to go copy pivot from. And we'll do our next bit of functionality, which is also just center pivot. And then because we've also done the American version, I feel like we kind of have to do it here. Okay, perfect. So we are using copy pivot 2 to take an item as a single positional argument, and then pass that through to copy pivot. And that is going to essentially say driver and driven to our node, which actually is the wrong way around. Just realized. Whoops. So we are saying driver driven, and we want to say, well, if we're driving, we want to say copy pivot to an item. So we're going to go the other way around. Okay, and then we want to actually then go item copying to our own object. Oh, that would have been an annoying one to spot later, but okay, good. We spotted it just before it became annoying. Now center pivot, again, using the center pivot command from Xform. So simple. Great. And now our last piece of functionality within this class, let's add another divider, is going to be a distance to. Again, an incredibly useful function, especially when building rigs. You want to know the distance between objects. You want to know how much you need to scale them, where to put items, how items should be spaced out, and that's essentially all comes from this nice little function down here. And now let's write it out. We want to again be well, driver driven, but we're again returning an int, so it doesn't really matter so much. Here we go, and here's our function. So we have a distance here. We could just return the method, and yeah, that could be fine. But what we're doing is we're just kind of showing again what it's returning. We're getting back the distance. So we should probably put that information. So let's go returns. Okay, exactly. Now let's create our function here. Brilliant. It created a function for us. It's not in the right place, but we'll move it now. So let's copy this code out, and we're actually going to add this to, so let's go from modules, and we are going to go utils.math import get distance between. Great. Let's copy that out, remove that. And then go down to utils, open up utils. And then within utils, we are going to go new Python file and math. Python file, brilliant. We'll just copy that in as is at the minute. And within DAG dimensions, we'll copy again string over. Okay, great. There we are. We'll need to import my dot commands as in. Also import math and import 6 for back compatibility. And then we will call these object 1 and object 2. Now let's write out our doc string for what we're doing here. Okay, so here's our doc string. And what we're doing here is we are going to measure the distance between the objects passed. Now, you can pass a list if you already have the X, Y, or Z. So that saves that being ascertained, but otherwise we'll just use Xform to gather that. So the args it takes are object 1, object 2, which are a string or a list, and the items to gather the position from within our list of X, Y, Z. And this returns a float, which is the distance in the scene between the items. Okay, let's write out our code. Okay, perfect. So get the distance between now. The first part of this is essentially just getting the position that these items are at. So that is what this class is doing. This function is doing. We are getting the position of each item in world space. And we are then checking if it is a string. If we passed a string, we'll use Xform. And if not, we're going to assume it's a list, because otherwise it'll just error out if you pass, say, a DAG item to it, because it wouldn't then obviously be able to do the calculations. Let's now make our next method. And this will accept two calculations. Call them and keep the consistency. Object distance 1, object distance 2. We're essentially going to return the 2D or 3D distance based on coordinates passed using these two lists of world space positions or floats. Now let's go through it. We're going to use a little bit of math down here, but I will talk you through it. Here we go. Let's look at our docstring first. Within this get distance between calculation, we are going to return either the distance between 2D or 3D objects based on the coordinates passed. Again, because the math isn't too different, we may as well put it all together. We're expecting two lists of floats, or integers they can be, but essentially two lists of numbers. And these are going to be the X, Y, Z positions in the scene. And then we will return the distance between. So in section 1 here, the difference of X and Y coordinates between the two objects are calculated. You'll see the distance 1 parameter, or the object distance 1 parameter, is always at the end. We're subtracting that after, essentially, to get the distance between the two items. That's consistency, either needs to be one way or the other. But you cannot have distance 1 subtracted here, distance 2 subtracted here, because that will be inconsistent. But, okay. And now, once we've got the X and Y distance between each other's calculations, or well, the X difference, I should say, what we're going to do is essentially check that our distance objects 1 is above 2, or above the length of 2. So it's not just X and Y. We're going to check that it's X, Y, Z. And if it is, it will assume that the calculation for, the object distance 2 is also above 3. And so we've got a 3-dimensional object to check the distance between. And in which case, we are going to use zdiff, essentially, to do the same operation again. So we've got X, Y, denoted by the indexing. Now we are getting Z. So the Z of object 2 minus the Z of object 1. And then we're going to use math square root, essentially to say xdiff times xdiff plus ydiff times ydiff plus xdiff times xdiff. And then all of that essentially will be square rooted together to find the 3D space. Because we have these 3 calculations together, that will give us the three-dimensional distance between the objects. But if we do not go through that if statement, what we will get is the X and Y. So just the 2D essentially position between those statements. Okay, great. So we have our math functions here. Now let us jump back to our DAG dimensions and just check everything. I think we've got everything we need. We've got our world matrix, where if there isn't a world matrix, we're going to error out and tell the user that there is none. And we have height, width, depth. We have the center position. We can then copy pivot as well. And we have distance too. That's perfect. Okay, great. Let's join me in the next lecture, and we will start looking at testing.